Hello, everyone, and welcome. Today, we are diving deep into one of the most powerful and revolutionary concepts in modern artificial intelligence, Generative Adversarial Networks, or GANs. Our topic today is simply titled, The Adversary. This isn't just about a single algorithm, it's an entire architecture built upon fundamental conflict, a constant battle between creation and critique. This conflict provides the engine for groundbreaking advancements. We are going to explore how this architecture manages deception, drives detection, and ultimately leads to truly stunning digital creation. It's a framework that forces two digital minds to compete fiercely, pushing both past the limits of what they could achieve individually, resulting in unprecedented levels of sophistication in generating realistic synthetic data. We will examine the rules of this adversarial game and see how a zero-sum battle can yield extraordinary results that are changing the landscape of technology, art, and science. Prepare to look at the process of learning and creation through a revolutionary lens. At the heart of a generative adversarial network lies a simple, timeless, and dramatic conflict. We are dealing with two distinct minds operating in one arena, both pushing against each other with opposing goals. On one side, we have the generator. Think of the generator as the master forger, the relentless creator. Its sole purpose is to create perfect, indistinguishable forgeries of reality, starting from nothing but random statistical noise. It strives for deception and aims to pass its creations off as authentic. It only learns when it fails to deceive. On the other side, we have the discriminator, the expert critic, the infallible detective. The discriminator's mission is pure detection, tasked with separating every single piece of truth from fiction. The key here is that these two components do not collaborate, they are locked in direct competition. Their failure is the other's success. It is through this escalating conflict, this constant one-upmanship, that something truly extraordinary and powerful is born. Artificial systems capable of creation. Let's formalize the roles of these two antagonists, the creator and the critic. The generator's mission is pure artifice. Its input is what we call a vector of random numbers or latent noise. It takes this raw, meaningless input and attempts to sculpt it into a convincing replica of the target data, what we call synthetic data. Crucially, the generator never sees the original real dataset. It only learns from the critique provided by its adversary. Its only teacher is the stinging feedback of failure when its forgeries are detected. Conversely, the discriminator's mission is pure, cold judgment. It is a sophisticated binary classifier. It receives input data, which could be either a true sample from the dataset or a synthetic creation from the generator, and renders a definitive verdict, real or fake. The discriminator's ultimate goal is deceptively simple, to never be fooled. As we see in the flowcharts, the generator moves raw noise to output, while the discriminator moves input to judgment. This structural separation ensures their continuous adversarial interaction. The interaction between the generator and the discriminator is not a truce. It is a relentless, continuous, a learning battle. The two networks are locked in what game theorists call a zero-sum game. Whatever one side gains, the other side loses. This conflict creates an escalating cycle of sophistication. As the discriminator gets better at spotting subtle flaws in the forgeries, perhaps recognizing a specific texture or pattern, it provides a more precise error signal back to the generator. This feedback acts as a teaching moment, forcing the generator to create even more realistic and nuanced fakes. This, in turn, forces the discriminator to sharpen its perception further, detecting even finer details. This cycle continues, spiraling outwards, until a state of equilibrium is finally reached. At this perfect stage, the generator's forgeries are so flawless and subtle that the discriminator can no longer reliably distinguish between real and fake data, reducing its judgment to a 50-50 guess. Game theorists call this point of perfect deception a Nash Equilibrium. This is the ultimate goal of GAN training, a perfect balance where the generator has mastered the distribution of the true data so thoroughly that its counterfeits are statistically indistinguishable from reality. In this adversarial system, every judgment the discriminator makes has direct consequences that govern the training process. These consequences are the four outcomes, two lessons that define the rules of engagement, framed through the lens of a classic confusion matrix. When the discriminator correctly identifies real data, that is a true positive. the system is working and no learning is required. However, if the discriminator believes fake data is real, that is a false positive. This is a critical failure, and this outcome trains the discriminator, forcing it to learn the tell of the new forgery. If real data is mistaken for fake, that's a false negative. Again, this trains the discriminator, forcing it to study authentic data more closely. Finally, if fake data is correctly identified as fake, that is a true negative. This is a win for the discriminator, but it is a critical failure for the generator, which learns from this mistake to create a better forgery. The key takeaway here is the imbalance. Two of these outcomes, false positive and false negative, train the discriminator, while only one outcome, the true negative, directly trains the generator. This inherent training imbalance must be carefully managed to prevent one network from overpowering the other. To manage the imbalance we just discussed and ensure that the adversarial training remains constructive, the process is structured as a disciplined, four-step dance of forging perfection, round by round. This iterative loop ensures both the generator and the discriminator learn at a balanced pace. Step 1. The discriminator trains on reality. It studies a batch of genuine, real data. If it mistakenly labels any of this real data as fake, a false negative, it adjusts its weights to become better at recognizing the genuine article. Step 2. The generator learns from failure. The generator produces a batch of fakes. If the discriminator correctly identifies these as fake, a true negative, the generator receives the error signal and updates its parameters to avoid that specific mistake in the future. Step 3. The discriminator learns from deception. The discriminator now studies this new, slightly better batch of fakes. If it is fooled by any of them, a false positive, it updates itself to spot that new trick next time, increasing its perception. And finally, step 4. The generator learns again. The generator gets a second chance to learn from being caught, another true negative test. By giving the generator 2 opportunities to learn for every 2 of the discriminator, we balance the learning pace and maintain the critical competitive tension required for successful GAN training. To truly understand the dynamics of this battle, let's simplify the arena and look at the blueprint. A skirmish in 2D, we start with a straightforward example where real data exists as 2 distinct, separated clusters of points on a 2-dimensional plane. The generator's task here is to take a simple input, 4 random numbers, and learn to transform them into x, y coordinates that accurately land within one of the 2 target clusters. Its network architecture is relatively simple, consisting of fully connected dense layers. The discriminator's task is to receive a single x, y point and output a confidence score, a number indicating its belief that the point belongs to the real distribution. Both networks, though simple in this example, are structured to engage in the exact same adversarial process, allowing us to visualize the learning curve clearly. This fundamental 2D example provides a necessary foundation before we tackle the infinitely more complex world of images and high-dimensional data. Now we can visualize how the adversarial process unfolds by closing the gap, epoch by epoch. We watch the generator learn how to map its latent noise input to the real data distribution. Initially, at epoch 1, the generator's output is random scattershot, distributed uniformly across the entire plane. The discriminator easily identifies these points as fake, but with each epoch, each full pass through the training data, the generator's creations become more focused. By epoch 5, the generated points, shown in crimson, start clustering, attempting to occupy the same space as the charcoal real data. By epoch 10, the generator has learned the separation and approximate shape, but perhaps not the precise rotational alignment of the clusters, a common intermediate stage. Finally, by epoch 20, the generator's distribution is a near-perfect mirror of reality. It has successfully learned the shape, the position, and the separation of the true data clusters. This visualization perfectly demonstrates the power of adversarial training to organize chaotic noise into meaningful structure, effectively learning the underlying statistical distribution of the data. The ability to generate simple 2D points is impressive, but the next arena, generating realistic images, is infinitely more complex. This shift requires a significant upgrade in our architecture, leading us to the deep convolutional GAN, or DCGAN. We are moving from points to phantoms. The DCGAN replaces the simple dense layers with convolutional layers, which are the building blocks of modern computer vision. These layers allow the adversaries to think in terms of local features, shapes, and textures, creating a feature hierarchy. The process starts at the lowest level. The first convolutional layer, CONV1, extracts simple edges. This information is passed to CONV2, which combines edges to identify textures. CONV3 then organizes textures into recognizable shapes. Throughout this hierarchy, the discriminator uses its convolutional filters, like the crimson filter scan seen here, to look for specific patterns or flaws. The generator now learns to sculpt complex images from noise, while the discriminator learns to see with an expert's eye, climbing the feature hierarchy to discern the highest level differences between an authentic shoe and a digital phantom. The result of applying this advanced DCGAN architecture is startling, illustrating the ghost in the machine. We tasked a DCGAN with learning from a dataset of apparel images. Importantly, the generator has never been explicitly shown a shoe, a shirt, or a bag. It only receives millions of pixel values and the raw feedback from the discriminator. Contrast the two sides of the screen. On the left, Epoch 1 shows pure static, random noise, entirely meaningless. On the right, after 100 epochs, the result is magical. The generator conjures recognizable, novel images of clothing: boots, t-shirts, handbags, jackets. These aren't copies. They are new, synthetic creations based on the underlying distribution of the training data. They are digital phantoms, imitations of a world the creator has never actually witnessed directly, achieved purely through relentless adversarial conflict and learning to defeat the critic. This capacity for de novo synthesis is why GANs are considered a breakthrough technology, enabling the generation of high-fidelity, complex, and entirely original data. Despite the extraordinary capabilities of GANs, the training process is fraught with pitfalls. One of the most common and critical failure modes is what we call the forger's tell, modal collapse. The generator, while intelligent, is inherently lazy. It constantly seeks the path of least resistance to fool the discriminator. If it discovers a single, perfect forgery, one specific image or a very limited set of images that consistently manages to fool the discriminator, it may stop exploring the full range of possibilities that exist in the real data space. Instead, it produces only those successful outputs, regardless of the input noise it receives. This is modal collapse. The generator has learned a single, perfect lie, effectively mastering a narrow trick, instead of learning the full, complex language of truth inherent in the dataset. This means that the diversity of the real world, the full spectrum of possibilities found in the original data, is completely lost in the generated output. Overcoming modal collapse is one of the persistent challenges in developing robust GAN models. The adversarial truce that powers a GAN is incredibly fragile, a condition we describe as a razor's edge, the unstable truce. GANs are notoriously sensitive to even the slightest imbalance, and small variations in hyperparameters can lead to a complete breakdown in training. If the learning rate is too high, or if there is an architectural mismatch, such as giving the discriminator too much network depth or adjusting the dropout rates incorrectly, one side can quickly overpower the other. For instance, if the discriminator becomes too powerful too quickly, the generator's creations will instantly be recognized as fake. The discriminator's output will always be zero confidence or a perfect identification of fake, meaning the generator receives no nuanced feedback. It never gets the useful error signal it needs to learn, leading to stagnation. Conversely, if the generator finds an exploit or a loophole early on, the discriminator may never catch up, resulting in poor quality outputs. Success, therefore, requires a perfect, delicate, and sustained balance of power throughout the entire training process. While the generator's success, creating statistically indistinguishable data, is a technical triumph, it has a profound, darker side. Endgame, a corrupted legacy. When the generator achieves its goal, the synthetic data it creates is not a perfect copy of reality. Rather, it is a perfect reflection of the training data, flaws and all. This means that any existing biases, gaps, or prejudices present in the original dataset, the bias in, will not only be learned by the system, but will be amplified and baked into every single new sample the generator creates. The discriminator, in its pursuit of perfection, only reinforces these internal flaws. Using this resulting synthetic data to train subsequent systems is extremely dangerous. It risks creating a self-perpetuating cycle of systemic error, effectively laundering bias into what appears, superficially, to be a vast, objective new dataset. The ultimate warning is simple and absolute: bias in, bias out. This highlights the critical need for careful curation of input data before initiating the adversarial training process. But let's return to the ultimate utility of this system of conflict. The battle eventually concludes. The discriminator, its purpose served as the quality control expert, is conceptually discarded. We are left with the victor, the creator, forged by conflict, the generator. This generator, hardened and transformed by the ordeal of having to constantly fool its expert adversary, is now a uniquely powerful engine of creation. It is capable of generating endless, novel examples of data that mimic the real world with stunning fidelity and accuracy. We built this system of conflict not for the conflict itself, but specifically to forge one half of it, the generator, into a master tool. The applications are vast and transformative, from generating new art forms and high-fidelity video to creating synthetic medical data for privacy-preserving research, accelerating drug discovery by simulating molecular structures, and building realistic environments for simulation and robotics training. The generator represents the mastery of data distribution, a powerful tool refined through digital warfare. We have reached the end of our exploration into the architecture of the adversary. What we have witnessed is how a system founded entirely on opposition, a zero-sum game between a creator and a critic, can lead to an emergent, highly sophisticated form of creativity. By pitting two competing neural networks against each other, we force them to climb to heights of sophistication that neither could ever achieve alone. This foundational concept of adversarial training has resulted in one of the most powerful and profound ideas in modern artificial intelligence. It gives us the power to create synthetic realities, data that is indistinguishable from life itself. But this immense capability is always balanced by the peril of the flawless fake, the ethical challenge of bias laundering, and the inherent instability of the training process. The ability of the generator to create is now almost limitless, but the story of how we manage this technology, the power and the peril, is only just beginning.